Okay.
All right. So yeah, I was just gonna ask what was it that you came in for? What did you want to go over?
I just wanted to go over the previous one because I didn't really understand um uh, two or three.
Okay.
So I don't know if it's because we don't have in-person classes right now. Um, but let me stream what I put down.
Yeah, sure.
Uh, for some reason Firefox is not showing up as a shareable screen. There we go. Do you see what my typing?
Yeah, I can see your screen. Yep. Okay.
Okay.
So you said you wanted to go over numbers two and number three.
I wanted to go over homework 2 and 3.
Oh,
Um,
homework two and three. Okay.
yeah, I didn't understand what to do.
Okay. I guess we'll start with since we only have about 30 minutes or 20 minutes. I want to start with whatever things you feel like are most difficult for you or hardest to understand.
Uh, so I was reading over this first question, and um, I so what I thought it was asking me to do. So it says make a truth table and then have the the inputs
And you want to
be
check if
one
the
or the
inputs
same.
are the same sign, right?
Yeah. So what I understood was that like make a truth table like standard. So I drew like all the values for 4 bits, and I
Right.
did the same thing for B. But as you can see,
They're kind of
they're always
matching
going to
up,
have the
right?
same sign. Yeah, so they're
So
always going to have the same sign.
the way you wrote it, so the point of a truth table is that you go through every possible combination. That's the whole point. When you go through every possible combination, then you can account for every possible combination. But the thing is, in your truth table, you actually haven't. So what you did is you paired up when A is 0, the number 0, B is the number 0. But on your truth table, do you have the case for when if A is 0 and the number B is 1?
No, I don't. And then
Exactly.
I was like thinking like I would have to write like a
A
huge truth
huge
table in
truth
order
table,
to.
yeah, you would. Because if you have 4 bits for A and 4 bits for B, that's a total of 8 bits. And 2 to the power 8, that's 256. That'd be a 256 line truth table. That's pretty rough. Um,
Yeah.
and so, as I'm sure you can tell, that's actually not really the intention here. You're not going to end up having to do that. So here's what I'm
Yeah,
going
that's
to
my
do.
thought.
Yeah, it would be kind of ridiculous, wouldn't it? Okay, so can you see my screen as well?
Sorry.
Yeah, you're good. No worries.
Um,
You can see it?
oh, why is it's not letting me zoom in on. Oh, there we go.
Uh,
The same.
okay, we're good. So, for a binary number in two's complement, like, for example, if I were to write let's do this number. Could you tell me what this number is, assuming it's a 2's complement binary number?
Yeah, it's A.
It's not. Sorry, what'd you say?
Said A.
That would be A in hex. Yeah, that's right. Now, if we were to interpret this as a decimal number, what would you tell me it is?
Um,
Well, what's the value of this bit right here?
yeah.
2, yeah. And what's the value of this bit?
Sound like not the camp.
Oh, yeah. I was just asking, what's the value of this bit over here?
Said 8.
Okay, cool. So,
And
if
then it's
this.
10, right?
Yeah, so if this was an unsigned number, it would absolutely be 10. However, what if this is a signed number, or in other words, if it's a 2's complement number?
Um, it would be -6.
Exactly. And the reason why is because the only difference is you add a negative sign for that topmost bit, and -8 plus 2 is, well, -6. And so what we know is that if this front bit, if the most significant bit on our number is a 1, that means that the number as a whole is going to be negative. So if this is a 1, then it's negative. If it was a 0 instead, then our number in total would be positive, right?
Mm.
So now here's what we can do. All we care about for this output, INSS, is just determining the signs of the numbers and if the signs are the same, right? Does this bit here impact the total sign of the number?
Mm.
What about this bit? And what about that one? None of them impact your sign at all. The only one that actually matters is the most significant bit. So what that means is, if you're on a truth table, instead of writing out A3, A2, A1, A0, etc., 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 you actually just need to include your most significant bit, because that's the only input that actually affects anything. All the rest are like don't cares. So I only care about the most significant bit of A and the most significant bit of B, which is B3. These are the only two bits which actually matter when we're comparing the signs of two numbers. So we have A3 and B3, and all we're going to do is say, well, now what's INSS? And just for reference, INSS stands for inputs are the same sign. So inputs, same sign. That's all that means. So now we can actually go through every possible combination. So I'll go and write that out in the truth table. Whoops. 1, 0, 1, 1. So now in this first case, are these numbers the same sign?
Yes.
Yeah, they are. What about in the second case? Nope. What about the third one? They're not. And in the last one? Yes, they are. Okay, so now we're pretty much done. All we need to do is turn this into an equation, and then we'll have the circuit, the digital circuit that gives us INSS. How do we go about that?
We could do a K-map, or we could just do, um, you just do like A3 bar plus, or A3 bar, B3 bar, and then plus um A3, B3.
That's exactly correct, yeah. So you could do a K-map for this, but since it's only 2 inputs, it's not a huge deal. If it was maybe 3 or 4, I would recommend doing a K-map. But for 2, there's really not much of a need. I will say that you can actually simplify this even further. This is the minimized sum of products form, but this also happens to be the exact same thing as an XNOR gate. So if we have A3 and B3 and we XOR them and then negate that, these two are the exact same thing. So recall that the definition of XOR means that one is true or the other is true, but not both. And the truth table for that would look something like this. So that's XOR.
And then XNOR is the even gate, right?
Yeah,
Is that what it's
exactly.
called?
Yeah, that's so you
Okay.
can think of this as odd parity and XNOR as even parity, or in another way of thinking of it, XNOR is just the negation of XOR. So XNOR is just going to be 1 0 0 1. Would you look at that? It happens that it lines up exactly with INSS. And so either of these formulations is correct. Doesn't matter what you pick, they both work. Okay, so any questions in regards to that stuff?
No.
All right. So that's basically it for part 1A. All you'd have to do now is draw out these two circuits. For the second one, it's just a single gate. It's the XNOR gate. So we have the XOR symbol with a negation bubble after it. And then we have those inputs A3 and B3. And you could also write the circuit out for this one, but I'll stick with the XNOR because it's simpler to write out. All right, now for part B, it's um, almost identical. The only difference is that it's asking you, instead of comparing the inputs A and B for the same sign, it's actually asking you to compare A to the sum of A and B. Now, in what ways is this different from what we did earlier in part A?
Oh, sorry.
No worries, yeah. Did you need me to repeat that? I couldn't hear you.
Um, I'm trying to figure it out.
Yeah, no worries. So, what's our goal for this second, for part B? What are we trying to do?
So we're trying to make a truth table for that like finds the output. We're trying to find if the A and the output have the same sign.
Exactly, if A and sum have the exact same sign. So, what changes in the process that we did before?
Um, we don't have to consider B,
We don't have to consider B, so instead of B, what would go here?
just the output
Yeah, and in this case, I think, yeah, they call
is
it
the sum,
sum.
right?
Yeah, so you'd say sum bit 3. But besides that small change, is there anything else?
Uh, no, I
No,
don't think
that's it.
so.
So it actually happens to be an identical problem. The only difference is that instead of using B, uh, bit 3 as one of your inputs for the XOR gate, you're instead using A3 and sum 3. So it's actually the exact same gate, exactly the same methodology and the same process. Only difference is you change this out to sum 3, and you call the output signal, a different name. It's called in out SS, and the reason why it's called that is because you're checking if the input and if the output have the same sign. So that's all that means. But part B is identical to part A, just switching some names around essentially.
Okay.
So now comes C, which is going to be different from the first two initial parts. So C here is asking you to do what?
It wants us to make a truth table for um, the output and overflow.
Yes, we need to check if there is overflow. Um, we don't. So here's what I'll say. Before we do this, I want to talk through a few examples and ask whether or not they're going to give overflow. So let's do a few here. So I'm going to do this number and this number. Now, just off the bat, would you be able to tell if these two would create overflow just by looking at it?
Um, Not until you add it and then check to see if, well, actually, wait, if they have different signs, then they're always going to be, I thought there's not going to be overflow.
Perfect. That's
negative
exactly what I
values.
wanted you to realize. This is a positive number. That's a negative number. Well, if one of the number is this in the negative position on the number line and one is in the positive position, and you're adding them, the result is going to be somewhere in between. We don't know where, but we know for a fact it's going to be in between. And it's not possible for this to go out of range of our bits, right? Our range would be somewhere over here in the negative section and somewhere over here in the positive. But if it's going closer to the middle, there's no way we're going to overflow. So, excellent point. We know that if we have different signs for our inputs, so if the inputs are different, that means no overflow for sure. It's guaranteed. Okay, so we know for a fact that if we're gonna have overflow, the inputs have to be the same sign. Sound good? Sorry, I think you might have cut out there. Are you still there?
Yeah, I said yes.
Okay, cool. So we know for a fact, like I said, they have to be the same sign. So let's look at an example of them being the same sign. So I'm going to do them both as negative numbers. And I'll do this. Now, I'm going to go ahead and add these real quick. So first column, 1 and 1 makes 0, carry the 1. 1 and 1 makes 0, carry the 1. This is going to be 1, carry the 1, 1, carry the 1. Now, there is a bit that came out, but remember that that doesn't necessarily mean there was overflow. How could we tell if there was overflow, though?
If the output was positive.
Exactly. So if this turned out to be a positive number, which means that this bit was a 0, then that means we have some garbage number. So if this, since we know this is negative, and we know this is negative, and we're adding them, the output had better be negative. If instead it's positive, there was overflow. Those are the two key insights we need to know to make this work. Sorry about that. So like I was saying, we know for a fact that if you have the same signs as your inputs and your output disagrees, if it's a different sign than those two, that means there was overflow. And so now that we have that known to ourselves, we're able to actually write out the truth table for this. So we care about two things. If the inputs are the same sign, remember we created a signal for that, INSS, and if the input and output match, that was in out SS. So let's write a truth table with these two as inputs, because those are the two things we care about, like we were just talking about. And let's see if we can figure out the truth table. So INSS and, whoops, IN out SS. And then we'll put an output column here, overflow. Actually, I'll do it like this. All right, so I'm going to write down all the possible cases. And I want you to tell me, row by row, whether or not there will be overflow. So looking at this first row, the inputs are not the same sign. Can there be
Oh,
overflow?
okay, I see.
Mm-hmm.
Oh, so no, there can't be.
Not possible. We don't even have to look at this. It doesn't matter what if the input and output are the same sign, because we know for a fact that the inputs themselves aren't the same sign. So in this case, and in this case, it's not possible to get overflow. All right. Well, now let's look at the next one here. So in out SS, because in both of these cases, we know that the inputs are the same sign, so there's a possibility of overflow. So inputs are the same sign, and in this case, the output is not the same sign as the inputs. Is there overflow?
Yes.
Yes, there is. Inputs match, but the output does not, so there is overflow. What about in the last case? The inputs match and the output matches the inputs.
Overflow.
No overflow, none at all. And so we get our truth table. It's actually going to turn out to just be a single AND gate and an inverter. If we were to write the equation for overflow, what would it be?
The INSS. INSS and then SS.
Exactly. So in SS, in out SS, bar. And so that's it. You would just then need to draw the circuit for that, which is just a single AND gate, an inverter at the front, and then you'd put your signals here, in, out, SS, and then you have your overflow. And that's pretty much it. That's the entire process, start to finish. Um,
Makes
sh-
sense.
she could have asked you guys to like just say create a circuit that detects overflow of addition of two numbers, but instead what she did was she broke down the process so that you can see how you might approach this yourself. Because if you were just asked to do it from scratch, the way you would approach this problem is you'd ask, okay, well, how do I know as a person when there's overflow? And we went through that. We did some examples and we saw, okay, if the inputs are the same sign, then there's a possibility of overflow. If the inputs are the same sign and the output does not match, then there's definitely overflow. And what I just said out loud is the same thing as this truth table. And so that's how you would go about the design from scratch.
So,
Okay, so have a few minutes left, so I can briefly go over number two, since I assume you have a question on that one.
yeah.
Yes.
So I know that for asynchronous resettable flip-flops
Yep.
that you have to change internal like circuitry the of it in order for the reset to apply
Yeah, to be asynchronous. That's right.
it to be asynchronous. So it resets whenever it's one. But I
Yep.
wasn't sure how to implement it because I know this is like the like without this R, like this is
Yeah.
the standard for.
So
So I didn't really know what to do with R.
yeah, no, that's a great question. So what you're looking at there, so on the left, on the very far left, you have just the standard flip-flop. And then what you're zoomed in on now, that's the flip-flop opened up where you can see two D latches back to back. You have to dive even further in. So if you look on just the left D latch, you can open up its internals, and what you're gonna see is you have two back-to-back SR latches. And so what I'll do is I'll draw one SR latch as it is, with its output Q. And the inputs of this, if we were to open up the left-hand SR latch, would look something like this. Here we have this input going to both of these, and this input going to that one. And this will be D, and this will be clock. I believe I might have these two switched around, but either way, that's not a hard change to make. You just swap the names. But what matters most is the part that we're going to be adding to this. So this is a zoomed in view of the D latch. And what we want to do,
This one specifically.
yeah, and we're going to use this, and it's going to replace both of the latches. You just need to make the same change to both latches. So we're just focusing on one, but after we finish editing this one, we're going to use this in place of both of the D latches. Okay, so we need to think about what we want to happen. We have an external signal reset, and we want it to behave as so. When it's off, when reset is 0, we don't want anything to change. We want it to do exactly as it would normally. If reset is on, then we want to reset the circuit. Well, in an SR latch, the way you reset a circuit is by making R a 1. That's just the way that SR latches behave. If R is 1, then the output Q goes to 0. Now, one minor nuance is that we can't have both S and R on simultaneously, because then we get an indeterminate answer. This is going to be some unknown voltage here, or some unknown
Okay.
logical value. So we just have to make sure that after we take care of adding some logic here, we have to make sure that we don't allow set to also be active by adding a little bit of logic here as well. So we'll focus on the first part, making reset R go to 1. So I'm going to say this out loud, and I want you to tell me what kind of gate you would put to make my words transform into a circuit. I want R to go on if the original circuitry is on, or if the reset is on. How would you translate that into a circuit?
are one and the original circuit is one.
So
Oh, and the AND gate.
so if I did an AND gate, let's see what would happen. Like this and like that. So reset is only gonna occur if you have an external reset and the original circuit wanted you to reset. What if this is off,
Um,
but this told
um,
you to reset? Would you still want it to reset?
no,
You would. So
yes.
the external reset is off, but the internal circuitry says we still want to reset, so you're going to reset. So in
So it's an OR
either
gate.
case, yeah, exactly. So you want an OR gate here. That's the job. That's the circuit that's going to do the job for us. If the internal circuit says reset, you're going to reset. If the external reset says to reset, you're going to reset, so you do an OR gate. Now let's consider the set over here. This is going to use reset as an input, so I'm going to have this wire ready, and now I'm going to ask the exact same question. If reset is on, what do we want to happen to this set?
You want it to be off.
We want it to be off. So what kind of gate do you think would be a good idea to put here?
Inverter.
So definitely an inverter, so let's invert the signal. Yeah, let's do that. It's a bad drawing. So we invert the signal, and we say, okay, now we have the signal inverted. So if reset is, whoops, undo that stuff. There we go. Now if reset is off, do we allow set to go through if this says yes?
Um, no.
Well, if reset is on, we definitely don't allow it to go through. But if reset is off, then we do, right? We allow whatever this is to pass through. What kind of gate would I put here to connect these two wires? What do you think?
Yeah. Yeah.
Let's try it with an AND gate, yeah, and let's analyze that logic. So let's see. If the original circuitry said we want to set, then this is going to be a 1 here. However, let's look at the reset. If reset is on, then this signal is 0, and what's going to be the output of the AND gate?
0.
It's going to be 0, so we're not going to set. And that's how we want it to behave, because if reset is on, we can't let set go to on as well. Now, what if reset is off? Then this input is going to be 1, and then what's this output going to be?
1.
It's going to be 1, yeah. In general, if this bit here is a 1, then we're going to follow the behavior of this bit up top. So let's see that in action. Let's say this was a 0 instead. What would this AND gate be?
Yeah.
It'd be 0. And if instead this is 1, then now this is a 1. So no matter what, if this is 1, the output is going to exactly match what we have over here, which is what we wanted to happen. If reset is not occurring, then we want to follow the behavior of this. If reset is occurring, which means that this is 0, then we ignore the behavior of this and automatically pass through a 0. That's the idea behind this. Now, this is pretty much all of the circuitry you need to add. This is it. So you have a single AND gate, a single OR gate, and this inverter here. And you would put this for each of the D latches, and then those new modified D latches, so I'd call this new D latch, I guess. This new D latch would replace both of the original ones that are in your D flip-flop, and now you have an external reset signal that can asynchronously reset the register, the flip-flop.
Yeah.
Now, the way we
And
went through
so
it, oh yeah, go for it.
I was asking, so this entire thing, this, both of these are both SR latches.
Those two are both D latches. If you open those up, if you open each of those individual ones up, you're going to look in this, and you're going to see one SR latch, and this is another SR latch here. The typical diagram for a D latch would be two SR latches connected together. Q, and then Q bar, SR, Q, Q bar. So this is a D latch. But what we did over here in this diagram is we just
Oh,
opened up
wow.
the left one. So it's a little interesting, right? You have a flip-flop that opens up into two D latches, and each of those D latches opens up into two SR latches. So that's how this works. That's the flip-flop. That's the latch. And this is the SR latch. SR, and the same for the others.
I did not.
Yes, so that's basically how it goes. There are modifications you can do to this, and if you look up online diagrams of the internal schematics of flip-flops, you can optimize the amount of gates you use by disregarding the structure. So the way we built this is we make one simple unit, and we build up from there and make bigger units and bigger units. But if you do the whole design from scratch, disregarding these units, you can optimize it a little bit more and just do it in terms of like a few 2 input AND gates, a 3 input AND gate, and then a few AND gates up here. And you can get a flip flop in just like, I think it's like 6 AND gates that are interconnected. But that's not too important for this class. The most important thing for you guys is to kind of understand how the simpler circuits work. So that's the breakdown. Flip-flop into 2 D latches, and though each of those latches breaks down into 2 SR latches. And you open this one up and that one up. You edit the internals to make it asynchronously resettable, and that's essentially it. That's the entire problem.
Each of these components will have the same clock.
Yeah, all of these components have the same clock still. That would be the signal here.
That's interesting.
What was I going to say? Oh, yeah. So we did the design verbally. Like I said out loud, okay, what do we want to happen if this wire goes high, that wire goes low? If I put this gate here, does that work? And it's fine to do things like that for simpler designs. It's kind of more trial and error than anything. But you could have also done this instead of verbally going through the combinations. You can do it visually or on paper by actually doing a truth table. That's another way to do it. What we did verbally, you could just do on a truth table instead.
Okay. Well, I think your time is up. We're over, huh?
Yeah, that's all right. For this question, for the what's it called for making an asynchronous flip flop, do you have any other questions for me?
Um, so so I was just supposed to make an like do the thing that you did with the SR latch, and then like that would be the answer. I wouldn't have to do anything with the D flip or with the D latches.
So yeah, pretty much. All you would really have to do is say, okay, this is my new D latch, just by
Oh,
adding in those 2 gates and the inverter. And so then you say, okay, now I have. Oh, let me scroll over. Now I have new D latch number 1. So new D latch number 1, new D latch number 2, and you connect them exactly as you did before with the D latches that you had in your diagram with the clock like this. So it's actually the exact same schematic picture. Where you have this is D, this is an internal node, and this is Q. So it's the exact same diagram you drew earlier. The only difference is they're labeled as your new D latch because you modified the internals, and each of them also has an extra input reset. So it's actually the exact same
oh,
diagram you drew, right? It's just you
oh!
had
I
to
just didn't
show.
have any terms.
Yeah, it's the same diagram you drew. It's just for you, you didn't show the edits to the internals. If you show the edits to the internals and then draw this new diagram over to the right, then that's basically full points. That's full credit.
It's too late to
It's too
go over the
late. Yeah,
conversation
it's too late to
internally.
resubmit it, but now you have a little bit of a better understanding for how to go through with one of these problems.
Yeah,
Okay.
I guess your Monday hours are are 5:30 to 6:30 or
Yeah.
5 to 6:30.
Every day, Monday through Thursday, it's from 5:30 to 6:30, um, and Fridays from 10 to 11. What was I gonna say? I do them on Discord if you aren't able to come in person, though I do recommend coming in person. It's just better overall if you're able to at that time.
Yeah, I can come in because tutoring for math that gets out of that. I've, I've been having to go a lot of tutoring.
Yeah, that's all right. Everyone needs someone to help you out. Um, okay, well, I'm gonna go ahead and end the office hours. Thank you for coming in, by the way.
Of course. Thank you for your help. It
Yeah, of
really,
course.
really helps.
Yeah, you're very welcome. All right, you have a good rest of your day.
You too. Bye.
See ya.